Welcome to deep diving into SST. So, SST is sum of squares total, and that refers to the total amount of variation in the outcome variable. And that is something that is important. When we think about linear regression and what we're doing, it's important to stop and really think about what's going on behind the scenes. And one way to start to do that, and one way to start to think about what linear regression really is to think about the outcome variable and how it moves. So right off the bat, there's a couple import statements, and let me just knock those out. So ISLR, we won't use any functions from it, but we will use one of its data sets. ISLR, by the way, is a great package for just data sets that are useful for lots of purposes. It's also a great book, so Introduction to Statistical Learning. If you come across that, it's free online, so you can find it, and it is just a wonderful walkthrough of a lot of different modeling techniques. What I'm going to, and theory as well. What I'm going to do next is just one more import. I'm going to bring in the whole tidyverse. We're going to use a little bit of ggplot here, and then one tidyr function I know is coming as well. So that will cover our bases all around. And what I'm going to say is data hitters. So hitters is active, it's in our environment, great, but come on, what is it? Well, it's a data set that we can see here from the structure function, that we can see things like the dimensions of the data set, and we can see that there are a bunch of baseball statistics going on here. And good news for you is if you are a baseball fan, then great, this will all just sort of click for you and you see what's going on. If you are not, do not worry at all. I assure you, you do not need any baseball domain knowledge to see what's about to go on with this looking at salary, which could be the outcome variable in a model. So let's take a look at the first 6 rows, and I'm going to stretch my console out, and I'm actually going to do that again, just make it a little bit easier to look at. And we can see the results here. And what these results tell us is, well, we know that with salary, there's at least one NA in there. There may be more. Let's find out how many there are. So we can do that with the sum function as shown up in the source pane now. I'm going to run that. And all right, so there's 59 NAs, and NAs aren't going to work for us for a mean calculation. If we try it, let's just see what happens. Oh no, okay, it does not work. We can find the mean for the rest of the values, and it's right there. It's displayed down in the console. But what we'll just do is we're going to use the drop NA function. So the drop NA function from tidyr, it will do what I want to do here, which is this is we're piping in hitters and we're specifying salary as the input variable to the function. It's going to remove any rows that have NA values and it will remove NE rows that have NA values for salary, but it will not go removing other things. So it's going to leave everything else intact, even if we have NAs elsewhere. All right, so enough of description. Let's run it. And so now we have the data that we'll work with the rest of the way. And we'll store this variable called average sal, or AVG sal. Let's bring that in right here. And that's just going to, we already know that value, it's shown right there, but now we've stored that as a variable, and we may want to use that again. So let's look at salary. And what we're going to do here, it might look a little strange. The notation there it's just written that way so that we can see that this single variable plotted in a scatter plot. Typically, we make scatter plots using geom_point, and we think about having numeric variables on the x and the y. Here, we're just looking at the distribution of a single variable, but we're doing it in a scatter plot, so hence the notation. What we can see here is we can see movement. So it's just as we move across the data set, each dot represents an actual point. It represents someone's actual salary. And of course, baseball salaries have changed a lot since this data set was even made. But at the time, some of these salaries were pretty impressive. These are measured in thousands, by the way. So we've got some folks here. We've got quite a few folks up in the $1 million country, and some folks that stand out as the highest. And then we've also got folks plenty of folks that are down here below $1 million, below $500,000, and the salaries, of course, are range bound by zero. Thankfully for these baseball players, none of them make a negative salary. So that is just a look at the distribution. And what we'll do now is we'll think about that in relation to the mean. So I'm going to run this next code here, this what you see on line 16 and line 17 up in the script, and I'm going to add a horizontal line that is depicting the mean salary. So green being the color of money, it seemed like an appropriate color choice, and so that is what's going on there. And now we have a little bit more of a sense of that movement. We want to think about this because, as I said at the beginning, this is thinking about the movement of the outcome variable is a great way to start thinking about linear regression and what it really is and what the linear regression statistics really tell us about linear regression models. So, and before we get into all that, we'll just start with this. Let's think about what we're looking at here. So we can see, I mean, the movement is shown. You can see that there's outliers that tend to be kind of on the high side. We got big groupings of numbers here, but we know that this is something that is going to differ quite a bit from player to player. We can get that just by looking at the graph, and so this gives us that foundational sense of what's going on, what do we expect. If we know nothing else, if we have a null model with no inputs, and what would we predict? Well, the mean is a pretty logical place to go there. But of course, a regression model is going to do something more because we're going to use inputs, and then we're going to make a smarter prediction than that. We will also use this to find SST. So the notes are here, and they're commented out in the script. SST is sum of squares total, and that is going to be, to calculate that, what we need to do is for every single point, for every single data point, we find the distance between it and that mean value, or the difference between those values, really, and we square it, and then we sum all of those squares. And by squaring it, you could say that it will magnify the impact of outliers, but the real impact, the true impact of squaring is that it's going to cure us of any positive and negative cancellation problems. Because if we didn't do that, we could mislead ourselves. Based on canceling, we might end up thinking that a value or a particular variable wasn't moving much at all, when in fact it was moving a lot. It was just the positive and negative movements were canceling each other out. So so where SST comes from, this is just designed to give you a visual sense of that, in that it's each of these individual distances squared and then summed. And then if you were wondering, once you get SST and you think, well, is that good? Is it big? Is it small? Is it good? Is it bad? That value, the value we get, doesn't have much meaning in and of itself. It's not, because it's going to vary based on what are the units of measure of what we're looking at as a potential outcome variable in a model, and then how many data points are there in the data set we're looking at, because SST would tend bigger if we're dealing with things measured in big units and we have lots of them. So there's nothing we can say about the value purely in and of itself, but SST will become useful for us when we calculate other regression metrics. That's when it'll have value. It'll have value proportional to other things that we'll need to find. So that is just a little bit of an overview and a sense of how to think about SST. And what I'll say here is we're going to find it. And yes, this could all be condensed onto a single line, but the point isn't to prove that. The point is to stop and really take that moment and think about what it is and where it comes from. And so we're going to just add this variable on to the end of the data frame here, sal_dist. And that is going to be the distance between the hitter's salary and the average. So we're going to just say that right there. And that is now stored. We've tacked it onto the end, and we still haven't squared it yet. So we've got to do that, and we'll do that here. And then what we can do, actually, let's take a little bit of let's take a look at least of the first few. So let's go head hitters again, and I'll stretch the console out, and we'll just see what we've got. So sure enough, right in line with what we did, we've got these sal dist values. And so the order in which these first two terms were written on line 24, or the salary and the mean, that order ends up being arbitrary because everything is squared anyway. But what we get are, we can see right here, the sal dist squared is giving us a sense of what each of these salaries is going to contribute towards SST. And SST is just going to be the sum of all those values. So I'll run that here, and we can take a look, and we'll see a number. And the number right now is really just a number. But what you can think about here too, sometimes I think extremes can be helpful in terms of framing what something means. When we stretch it out in a certain way, or we shrink it a certain way, what happens? Well, one thing you could think about is, what if there were no movement? What if the outcome variable were just completely consistent? It was always the same number. Well, that might sound a little silly. You might say, well, why would we bother with a regression model? Well, we shouldn't really. Then if it really were always the same, we should just always predict that outcome and always be correct. But to think about what the question's saying, let's think about that extreme. If there's no motion of the ocean, if the waters are so calm that the y variable never changes, well, then SST will just be 0. There's just nothing to speak of. And what you can think about is, as the data set gets more and more varied, as it gets more wild, as the seas get crazier, what happens is SST is going to become larger, and that might present more challenges in terms of being able to accurately predict what the outcome variable would be as SST gets crazier based on more difference. But that is it. That is a look at SST, what it is, where it comes from, and then we'll dive in some other videos a little more into why we care and when it becomes more useful to us in relation to other values. So thank you very much.